Okay, well, introduce yourself.
So now we are scaling back the ambitions a bit from the previous talk where it was about static analysis of software to just use using the contract-based programming used in 2012. I've tried sort of to form this as a tutorial. If we start out more as a formal presentation, then I have an example provided by Didier, who's going to give the next talk. So I didn't make up an example I feel for the task, but I had to work on real code. But I'm going to talk about how you should use, how I think you should use aspects of contract-based programming in Ada 2012. Just so I sort of know, how many of you have not programmed in Ada at all? Okay, that's good to know. Did you happen to hear either Jean-Pierre's talk this morning or the previous one? Okay, so I'll be a bit more detailed about this title. Me, I'm an independent consultant, mostly doing software development stuff, but also interesting things like inspecting oil platforms and writing parts of computer games, and studying finance. Well, since you haven't all heard about that much about Ada before, I'll just take some of the reasons why we should be using Ada, at least the design arguments for Ada, about seeing programming as a human activity, about reliability, and about maintenance. Contracts in Ada, that's mostly about reliability and maintenance, as the contracts is a form of documentation which has the added benefit of actually being checked by the compiler either at compile time or runtime, improving reliability that way. That's a very short story about Ada. Then I have my presentation of Ada in a single slide. It's not enough to learn the language, but you get an idea about it. It's a procedural programming language with support from object-oriented programming. You're not forced to use object-oriented programming, but you can do it. There's what Ada people call modular programming. You can separate your project in packages, child packages, and you can have individual standalone subprograms. There's generics, which is an alternative to object-oriented programming for generalizing your solutions. And one thing that I like very much, and which is also very relevant about contracts, is that's the separation of declarations of subprograms and packages and the actual implementation of them. So first you specify the interface, and then separate from that we write an actual implementation where you, just to make sure you're doing the right thing, you have to repeat the basics of the specification again. And then, well, it has concurrent, distributed, and real-time programming facilities built into the language, not just but not as add-on languages, but actually as a part of the language specification itself. And then, in my opinion, types are distinguished by name rather than just by what values happen to be possible to put into it. And it's composed by composite types, like what we call classes, if you're not a major programmer, and for symbol types, like various integer, floating point, and operator types. And the most recent standard was published more or less on Lady Lovelace in 19. What is it? 198 birthday. 15th December 2012. This is from 14 but then the 2012 standard is only one in the series, and some of this, which is new, which is exactly about contract-based programming, that's the ability to declare pre- and post-conditions for subprograms, which is, as a minimum, formed as runtime checks on the state of parameters for subprograms before and after call. Then there's type invariants and subtype predicates, which are kinds of constraints which should be consistent for all objects of this type at all times. The differences between these three is that type invariants that are checks on private types where you have hidden the implementation details of exactly which components exist on. Where predicates, that's for technically for subtypes, but for types where you have visibility of the internals. And they act more as constraints, and the difference between dynamic and static, that is related to how easy it is basically to do a compile time analysis on them. I have an example later on where you'll see that the compiler actually already looking at GPO 2013 edition can catch the compile time programming error in a case with standard subtype predicates. Hopefully in the future we'll have more of the Sparre tool facilities migrating into the compilers, so we'll have messages when you compile that, well, your program will fail when you're going to run it at this line because you're not fulfilling some condition. But we're not quite there yet. Say you'll go back to Paris and work on it soon.
If we do that, the thing is that people will say, oh, the compiler is supposed to roll now.
Well, yes, I know. So now you still have to run various tools besides the compiler to get some checks on time. But besides all this new and fancy stuff, which Ada programmers make us before, there are all the old stuff. We have the name primitive types. If you have specific type, even if you have another type which can have exactly the same values, you can't just copy between objects of the two types. You have to make explicit conversion. You have parameter passing directions on your subprogram, so you have to tell explicitly if an argument for a subprogram is parameter going in, a parameter going out, like the one that's going both in and then out after some manipulation. And then we have range checks on arrays. So you don't accidentally, or on purpose even, address outside an array. And then we have subtypes, which is basically you can make, having an existing type, you can make a subset of it with ranges. And then there's some cases where you have static tests, like that a case statement covers all the possible values of the argument for the case statement. You'll get a complaint and a compiler error if you don't cover all the possible values. And some of this is compile time checks, some of this is runtime checks. But it all helps catching errors earlier, and the earlier we catch the errors, the better. I've used contracts on a science project for the last year and a half. And I must admit that even though we're using them, I'm not sure we've actually caught any errors directly by the compiler saying you did something wrong. I must admit that. But it could be because we're good programmers. It could also be because we're not applying the contracts that much yet. So now I'll start going through each kind of contract elements we have in ADA 2012, come up with some comments and a small example. We'll start with precondition, and from the rationale for the ADA 2012 standard, it's an obligation of the caller to ensure that something is in order before you call the subprogram. And it's a guarantee for whoever implements the subprogram that this will be true once you're called. I just came up with an example. Even in ADA 2012, they haven't actually put any of these contract aspects on much of the standard library, so I decided I would take some examples from the text.io API data. So we say we want to put a string to a text file. Well, we better make sure the file is open first. So this is one example you could put in on a precondition. Still, in this case, we could of course have a race condition that, well, once we call it, it's okay, but the OS dismount the file system or make something other strange things meanwhile, so the operation can still fail in this case. But it's a nice minimal requirement at least. Similarly, we can look at post conditions, what the state after talking to us when we call a subprogram. That's an obligation of the implementer of the subprogram to make sure that this is true once the subprogram returns. And it's a promise, on the other hand, to the caller that this is how the world will be afterwards. And I decided then, okay, let's put line again in the text.io API. And Ada has, depending on your view, a nice or an annoyingly positive feature of keeping track of line numbers in the file when you're writing to it or reading from it. So actually, we can say that after you've done a line, the line number has been incremented by 1. So that's an example of a post condition. Here, I reference the value of the line number before calling with this -old. Yeah, I'm sorry, I'm not going to teach you the details of the syntax of Ada in this talk. That would take more than an hour. But there are lots of good references for that. That was pre and post conditions. Then time invariance. This is an example I've adapted from the Ada 2012 rationale. Imagine you want to have here. We want to have a time able to represent points on the unit list. I wasn't a mathematician once. So points is here. We can start by just saying, well, we do it in rectangular coordinates. Here. But then the flow then it could be anywhere. Then we put limits on -1 to 1, and we get it into this box here. But we don't want it to end up on here. We can do that with a time invariant that the distance from the ergo shouldn't go beyond 1. So now we have a type here for managing points on the unit disk. Of course, there could be any kind of condition here. But the point is that this is something that the compiler now is obliged to ensure for objects of type list.pointer that it always has to be true. You could actually variant at this point derived from one that was just an arbitrary point, where you said, okay, it can be anywhere as far as our floating point type can represent. And then this is a subtype, the subtype string. Then the other kind of variance that's dynamic subtype predicates. That's kind of constraints subsetting subtypes. I picked a nice little example here. A prime. It's an integer. It can't be less than 2. And you can't have any factors into the number which are different from 1 and the number itself. Which, if we look carefully here, we say that prime modulus n is 0. That happens for some n from 2 up to prime minus 1. Then it's not, our dynamic predicate is not true. So now we have a subtype of integers, which is only the primes. Unfortunately, we can't do fancy stuff like looping over a subtype with dynamic predicates. You can do that with static predicates, but not dynamic predicates. But you can at least make, now you can just, the lazy test now for which integers are primes is to just loop over all the integers and see if you can, if it's in the subtype prime. Of course, it's not necessarily computationally efficient, but that's a different matter. This is an example from an actual project where there was a decision somewhere that these organization UI could not be longer than 256 characters. And to avoid that, we accidentally in our program tried to put longer strings into our database. We made this subtype where we put in a dynamic predicate and the length of these strings. In older versions of Ada, you could do something similar by creating a bounded string which could have length up to 256 characters. But all the work of doing that, this is much easier. And then, I said before, it was dynamic subtype predicates. Static subtype predicates are more limited in what, basically it's the same, but it's more limited which expressions you're allowed to use. You can do anything where your subtype is in a statically defined set or part of an otherwise static expression. There's some operations you can do at least. It's not all. But this is one of the cases. Look it up in the reference manual when you get to it. I was in Mauritius recently working for a small data company there. So I decided, well, we'll make a nice example with the summer going from November to April. I was there in the winter, but that's a different story. So now we have a type of month, just made them short. This is an example of enumeration types in Ada. And then I make a subtype where I say, okay, the summer month, that's from November to December, and then from January to April. And then I declare an object. And then I accidentally switch back to northern hemisphere mode and say, well, July is a summer month. But trying that with the compiler, you get the warning that it doesn't work. You get a failure because July is not the summer subtype. There's a similar example in the 2012 rational, but it's written by an Englishman, and he's clearly not used to the concept of that's the summer can go from November to April. So he does it with a window from December to January, to February instead. The effect is the same. And then I talked about coverage check. Here I have a, well, not very nice example of a case statement. Level declares the level of some logging messages, the severity level. And then we say the different operations where to send the messages depending on the level. It's split out in the case statement. But what would happen if I accidentally forgot to put in the alert level? What would happen would be that the compiler would say that I'm not covering all the possible values of the type of level, and it would stop compiling my program, telling me I have to go here and do something. It's not directly contract, but it's a very useful static implementation check. And it relates to the subtype of this value you put in. So that was a quick overview of contracts in Ada 2012. Now it looks like he's seeing if I got everything included. Yeah. Okay. Then I've done my best to put some guidelines together to get a consistent use of contract-based programming in Ada. When I started, I just put things in at random when I sort of felt like, well, we can put something in here. But it's better if you do it consistently across the application or your library. And the place I like to start when I'm programming, that's with the types. So make sure that you make a good detailed declaration of the type and its constraints. You declare type or subtype depending on the requirements of compatibility with other types. If you want to be able to pass directly, or if it should be really a unique type that you should accidentally copy back and forth. You can put appropriate constraints in your values. I had the example with the points where I put the constraint that the floating point coordinate shouldn't be less than -1 or larger than 1. As an example. And then you can add extra examples, extra constraints, if it is relevant, as predicates or invariants in the type. But I think you'll see that in many cases you don't really need that. This is enough of a contract for the type. I go back to my integers in my prime example. It's nice. We start out with this prime integers. And I decided here that, well, it's really an integer. It's not that special, so it's just a subtype of integer. If I thought it was really something special, I would say prime, type prime, this new integer, and it would be a new type, just happens to be derived from the integer type. And then there's this about primes being larger than 1. I put the range constraint on. And primes are nice because that's not enough. We also need to keep track of the only factors is 1 and the prime itself. So, an example, maybe contrived, at least I have to say so. I haven't used it in real code. I did use Sparre once to validate application to find primes. And it found an error I hadn't found in my testing. I was impatient. If I had let it try to run to the end, it would have failed around there because there was some mismatch running over the edge of the number of integers to be processed. It took some time to figure out that it was that Sparre was telling me was wrong. But it's definitely useful, and it's useful in cases where you might not have the patience to find it by testing. I know also that the Sparre people have been involved in testing a cryptographic hash function where there's a bug in the reference implementation. If you give it 2 to the 64 byte long data sets to hash, it gets the wrong value. And nobody apparently have tested that. So the bug is still there, even though it has been reported. But then, back to the main story. Now we have declared our types. The next step, that's the subprograms which are going to operate on these types. I'm not going into detail about the subprograms themselves, but when we know which ones we need, make sure that we are as specific as possible about the arguments. So we select the proper direction of each argument. And we select as specific as possible a subtype for each of the arguments. And if we with plain subtypes can't do enough, then we can continue and use pre and post conditions to declare even stronger constraints. In my example here, that's nice, simple, and the compiler should probably be able to figure it out. It's an example of increment. Procedure to increment the counter. The counter has to be incremented, so it first has to go in, be modified, go out again, and we say we want to do it with arbitrary steps, so that's something that just has to go in. And well, it's both integers. Well, actually, counting, we start from 0. There can't be less. That's natural numbers. And we say we're incrementing, so the step can't be 0 or less, so it's a positive number. These are predefined subtypes of integer in either language. So now we've put some constraints here on the counter and on the step size. This is something you've always been able to do in Ada. Some of the next steps that here, that's 12 specific. Well, we put in a precondition. Since we're going to increment, the counter can't already be the last possible value of our integers. And the post condition, well, it will definitely be more than 0. But we can do better than that if we really want to. So we can go a step further, say we should have steps which will make the counter go beyond natural last. The other one here is really a subset of this one, but that's a math exercise, and we're not about to do that today. So that was the first step with our subprograms, looking at the arguments. The next step, that's what are the requirements of our subprograms? Which preconditions do we have? Are there any special requirements which should be in place before we call a subprogram? Can a subprogram only be called once in the whole run of the application? Can it only be called when the application is in a specific state? And this is what we can document preconditions to the subprogram. And here, first, I go back to the text.io example, where writing to a file we have preconditions. The file should be open, but it should also be a file that we can write to, so either that would be an alt file or end file mode. And another example that here, I imagine I have a variable, a function telling me about the state of the system, and initialize should only be called if the system is in the non-initialized state. When I get to the working on an actual live source example, we'll have something like that to look at, because there's a bug in the API that DJ has provided me with. So that's good. I like that. Things to work on. And then the next step, that's looking at likely sequences of calls. So we have our types, we have our subprograms, functions, procedures. What are the likely sequences of calls in these subprograms? And specifically, with these sequences, as the promises from the first one, does that include the preconditions and the next one being called so on in the chain? So we want to call, what should we say, initialize. Box, say, shut down. If part has a precondition that the system is initialized, and initialized doesn't have the postcondition that the system is initialized, we have a problem. So that tells us how we figure out how to add those conditions. We can see that here's a find at the end here and here we have the precondition initialized. Shut down. I suppose no precondition. This says, okay, would it make sense to say that the system is initialized after we initialize it? So we put that in as a first condition. Oh, yeah. So it doesn't change it, so it's still initialized. This is a case where Spark will help us even further, because Spark tell us that we're not messing with the initialization state function. And shutdown is non-initialized. Maybe it might be non-initialized, allowing us to run and initialize again. So we could have things like that set up. Sorry, I do have spikes also. That's a different example. Here we have another call sequence that's open a file, write to a file, a hidden writing, close a file. That should actually be the last point. Then it will take more than one slide. So we say put line has a precondition that the file should be open. Well, that means that open should have a postcondition the file is open. And that makes sense. We want that. Actually, the way the word works is, well, it might be open, or it might raise an exception. There's more than name error that we can get out of open, but I didn't have enough lines here. So you have, yes, we can call open and then put line, but actually in between we have to be prepared either that we end up down in the exception handling step or do something else about the exceptions. But if the flow goes straight through the open line, then we'll know that it is open when we get down here. Everything's fine. But this exercise, in a way it's relatively trivial. The hard part is actually making up these sequences of likely sequences of calls. Once you have the likely sequences of calls, it's really trivial. Mostly trivial. But still, you have to do it. And then it's time for some source code I didn't write myself, so it's not written quite for this purpose, but rather for static analysis experiments. So this is a simulator of a sand-pile experiment. So you're dropping sand down from the top and it's falling down, and when the slope is too steep, the sand will fall down either simply not to one side, always to one side, or in cases there'll have to be a decision if it goes to one side or the other. This is just to show the running application. Then I'll start by showing you the main body of the system. So he starts his cellular automation, and then there's a loop of updating it, adding a brain next, and then showing, and then exiting, taking a register, and then clearing stuff up at the end. But what happens if we somehow forget to call the start? Steady automation. I'm just commenting it out now. Then what we get an access check, which means that there's a pointer somewhere inside this library that we're using, which is not, which is null and has not been allocated an object on it. It is, of course, a way to stop. Another option could be that we actually make sure that we keep track of the state of our simulator, like this, and then we'll still get an exception, but it will be caught further out in the system. It will call. It will be caught when we go out the end outer loop, really. When we try to add a brain, that we'll know that we're not initialized. So it's in source, it's a different place. It's in microseconds of operations on the computer. It's not a big difference. Once we get the checking tools in place, but we run the Sparre verifier on it, it will make a difference. Then we'll get a compile time check if the preconditions don't match up. So what I was planning to do was I just, as a demonstration, go in and put in some state management, like I've indicated here, in this library. And show you that then we get, well, what we get now is not a compile time error, unfortunately, but we get a different error message. use some smaller font. It's big enough that everybody can read, right? And it's still big enough that everybody can read. Also in the back row. Okay, good. So this is the specification, the external specification of the cellular automator simulator. It sets up a lattice that it's operating on. It has a constant saying, the source where we're putting in sand, and some parameters shaping the decisions. That's part here. And then we have the actual operations. Starting and stopping, adding a grain, going to the next step in the iteration, and showing the correct state. But without any pre and post conditions. So what we could do is that I would start to say we define a type describing the state of the automaton. And what will it be uninitialized? It can be switching and initialized. So this is just the type, the kinds of states we say we can be in. I cheated and looked inside it, and as far as I can see, after we've had start, we can start it up again. That's why I don't have a separate state for being uninitialized beforehand and having started again. Then we want to be able to check, ask about the state. So we just specify a function that returns an automation state. So now we actually have enough information up here that we can start to add post conditions first to each of our operations. We can see the follow procedure. So we say, well, there's no parameters, so there's nothing there. It's all working at an internal state. So we say our start procedure has a post condition, which is that it is initialized.
State equal initialized?
What?
State equal initialized?
Yes. Exactly. If somebody remembers. And starting similarly. Now it's uninitialized. And the other ones, they don't change anything. So this is what we have. My first take on what are the post conditions. So going back to that's because I say, what do we do? Now, I'm not doing it right. Because really what we should say is that what do we need? No, you didn't catch all the errors literally, because no, this gives yes. Then adding a grain, we can only do that. We saw we got the constraint error. We have the precondition that we are initialized. State is initialized. And the same is the case for next and showed. We're not initialized, it doesn't work. So, how complete are we now? We basically we say that what we do is we say start, and then we say add range, then we say next, and then we may say show, and then we may go back here sometimes, and then sometimes we say stop. And preconditions here, that is initialized. And we can't, the stop actually attempts to deallocate. And if it tries to do that, we better be initialized. And start, it's good to be uninitialized because otherwise I know there'll be a memory leak. And if some of you are wondering why I put in the switching state in between, it's because behind the scenes there's actually tasking. It's a parallel processing program. So in case some function somewhere might be asking while we are changing the states, I suppose we better have the possibility to say we're switching state at the moment, which means that I really have to make the variable where I keep track of the state should probably be atomic. And we could just put that variable in here. Notice this private, the package specification is separated in a public part, which is the one that the users of the package can see, and a private part which focuses on details about the data modeling. But you can also keep certain variables in the private part instead of moving them all the way to the implementation. Who's keeping track of the time, by the way?
10 minutes left.
10 minutes left.
Actually, 5 minutes.
5 minutes.
If you allow time for questions.
We should have at least time for questions.
Then we should have
So, when we go through here, so what did we say? We said now we have also variable keeping the state. Start. Well, it is initialized after we've done it. But before we said it should be uninitialized to avoid memory leaks. Then we've set adding a range, next, and show as preconditions about being initialized. That's good. And we're better putting what we have on here. So start, after we call start, we are initialized. And after we call stop, we are uninitialized. So we have the precondition, for this sequence we have the precondition of add is included in the first condition of start, that's fine. Next has a precondition, it's not included in the first condition here. If we had control of data flow, it wouldn't be a problem because we know that it doesn't change the state. But we better here go in and say, well, actually the post condition of and we're still initialized. Just to make sure that we don't get a problem with next. Now we actually have an option to do something interesting. We should really implement this function here, giving us those making states. It's very simple. And I did say something about making current states. Now we've set what we do. Now we can build the program and run it. We get an assertion failure, which basically means that one of our contracts were wrong. And it says cellular ultimatum ADX40. Anybody who kept track enough that they're able to tell us which one that is? So, add a grade fails. Actually, I'm surprised.
Because you removed the initialization.
Not changing the value. We're not never changing the state.
Yes, but no, what surprises me is that I'd expected the post condition and start to be the one that failed.
But you never call start. You removed the call.
I removed that call. That's why, yes. So maybe we should go in and, so we get the right error, yes. So we go in and activate start. And now we have something that locks up. Do you have any, where did you go? Are there any race conditions in your application, did you?
Yes, sir.
Okay.
Race conditions.
So now we get an assertion failure, but at least if the compiler works, and we know we should get an assertion failure on exiting automation start. So now we go into and say, now that we talk about the state, we'll actually go in and say, so we switch. Now it runs. And now when I ask it to stop by pressing Q, we will enter stop. And stop will start fine, but on exit we have not set it to uninitialized, and then we should get an assertion error. Failing post condition, line 37. Yes. So we can see that we can play around with these between post conditions. And we still have a few seconds. I'll go and notice. No, I'll stop now. Bad style. In Ada, you can declare enumerated types as I did for the automation state. So a case like this, you really make a state type which is empty, settled, and then you write out this representation array with the characters, also making sure that you set that empty gives you space and settled gives you the lowercase o. But that's it. And there's not so much, but most about things I've said. And you can find source code examples here, my website there. And I'll put my slides on my website.
All the slides will be put on the
Yeah,
website.
I'll publish mine in a few minutes. Now I know how they look when I get the presentation. Any questions? Any which are short enough?
I was just wondering about this example with an invariant that guarantees that a point is on a unit disk.
Yes.
I was wondering when is this check actually enforced and how will that impact performance? Or whether I can even use such a, complicated, let's say, invariant in practice.
It is forced, let's see, subprogram exit, type conversion,
Yeah, it's basically enforced each time you access the, let's say, the interface, which is anytime you have
each time you do something which could change it.
right. Which is, yeah, the conversion.
Type conversion and returning from a subprogram.
The return from the program.
One that has it as a return value or parameter.
Yeah.
If it's just an in, nothing will be done.
Yeah.
But yes, it might impact performance. My view is I prefer a slightly slower program which gives me a correct result than one that gives me an incorrect result. If I want one that gives me an incorrect result, I can do it pretty quickly anyway.
I'm sorry I missed the beginning of your speech, but I'm an FL programmer, so we have
You've had stuff like this for a long time.
Like for a long time. One of the issues in the implementations are about recursive calls in evaluation of the precondition or post-condition.
Yeah, it is resolved. I can't remember the details, and I'm not one of the people who have to implement the compilers. Jose, can you remember the details of how the standard resolves the issue?
No, I don't remember that.
I'm pretty sure I've seen something exactly about how to resolve that issue, but
Yeah.
I can't remember the details.
That's true.
So, I'm sorry, I can't help you with the details there. I wouldn't mind trying to figure it out later on. Yeah, you?
I think the problem you mentioned is when you have something like stack full with a precondition not stack empty, and stack empty with a precondition not stack full. That's right. And in ISO, if I remember correctly, assertions are disabled while you are checking another assertion.
Yes, implementations differs depending on compilers, but it arrives when, for example, you say, okay, my result is not the result of the function that is prefixed with not.
Well, that's what I said. Typically not full. Empty implies not full, and full implies not empty. I remember we discussed that. I mean, during the design of the language, I can assure you that there is nothing like disabling in certain contexts. Now, how you resolve that one? I mentioned this morning that the reference manual is freely available.
Yes.
But also you have an HTML version of that, and you have another one which is called the annotated reference manual. And in addition to the normative text, you have comments that explain the rationale, the decisions, and the things that have been discussed when designing the standard. So in a case like that, the best thing is to refer to the annotated reference manual. There is certainly something about that.
It doesn't say recursion
You have it?
here.
Yeah, but do you have the annotated?
I haven't got the annotated installed, no.
No.
I put a pause, activate the network.
Well,
check.
just type annotated ADA reference manual.
Yeah, but I turned on the network so I wasn't distracted while presenting.
Well, maybe you can take that offline.
I think we should do that offline because we have another presentation coming up now. Let's look it up. And
So the next presentation, is that more about